In this video we're going to introduce some of the important language used with probability and sets. So, within probability the fundamental idea is that of a random experiment, and that is simply an experiment whose outcome cannot be predicted in advance. The sample space, or the outcome space, of a random experiment is simply a list of all of the possible outcomes of that experiment, which will probably be written in set notation. An event is simply a subset of the sample space. And a probability model is a way of measuring how likely events are to occur. An impossible event has a probability of 0, and an event that is certain to occur has probability 1. All events will have a probability that lies between 0 and 1. At GCSE, you'll have often used the idea of the probability model where the sample space consists of equally likely outcomes, in which case the probability of any event is the number of ways in which the event can happen, divided by the total number of possible outcomes of the experiment. So, if we consider the experiment where a pair of normal fair cubical dice are thrown, what is the probability the total score exceeds 9? Well, all of the possible outcomes of the experiment can be shown in a diagram, a bit like a graph, where each dot represents one possible outcome. The outcomes which give us a total score that exceeds 9 are the 6 outcomes in the triangle there. So we can say the probability that the total score exceeds 9 is 6 out of the 36 possible outcomes. In other words, it's 1 in 6. Now we need to introduce a little bit of language about sets that you may or may not be familiar with. If A and B are subsets of the sets of all possible outcomes of an experiment, then first of all, A' is the complement of A and consists of all of the outcomes that do not belong to A. So let's have a simple example to deal with. Suppose that we're dealing with the experiment of throwing a normal fair cubical dice, in which case the sample space is simply the set 1, 2, 3, 4, 5 and 6. If A and B are the events, A is the event the score is an even number, then A is represented by the set 2, 4 and 6, and if B is the event the score is a prime number, then B is the set of numbers 2, 3 and 5. Remember that 1 isn't a prime number. Then we can represent the two sets A and B in a Venn diagram. The number 1 isn't in A or in B, so it goes outside the two circles. The number 2 is both in A and in B, so it goes in that area in the middle of the two circles. The number 3 is in B but not in A. The number 4 is in A but not in B. The number 5 is in B but not in A. And the number 6 is in A but not in B. So there's my Venn diagram showing the sample space. A' is the complement of A, so that's everything in the sample space that is not in A. Well, A was a set 2, 4 and 6, so A' is going to be 1, 3 and 5. In terms of the Venn diagram, A' consists of everything which is not in A. So on the shaded diagram there, I've shown the set consisting of A dash. A cap B, if you like, A intersect B is the intersection of A and B and consists of all of the outcomes that are in both of the sets A and B. Now the only element that is both in A and in B is the number 2. So A intersect B is simply the number 2. In terms of a Venn diagram, A intersect B is going to be the common area between the region representing A and the region representing B. A cup B, or A union B, is the union of the sets A and B and consists of all of the outcomes that are in A, or in B, or in both. So in this case, A or B is going to be the set 2, 3, 4, 5 and 6. It's everything except 1. Because 2 is in A and in B, 3 is in B, 4 is in A, 5 is in B, and 6 is in A. So A union B is 2, 3, 4, 5 and 6. And in terms of the diagram, A union B is represented by the combination of the region A together with the region B. So here we've got a table showing some of the subjects being studied by a group of Year 12 pupils. One of the pupils is picked at random, and the events M, E and C are defined by M, the pupil chosen studies maths, E, the pupil chosen studies English, and C, the pupil chosen studies chemistry. Now just looking at the table, we can see that the probability that M occurs, there are 6 pupils out of the 10 studying maths, so the probability of M is 6 over 10. Similarly, the probability of E is 3 out of 10, and the probability of C is 5 out of 10. Now we can also, from the table, work out the probability that M doesn't occur, in other words the probability of the complement of M. Now we know that 6 of the pupils study maths, so 4 of the pupils don't study maths. So the probability of M dash, the probability the student picked at random does not study maths, is 4 out of 10. Similarly, the probability the student picked does not study English, or the probability of the complement of E, is 7 out of 10. And the probability that the pupil doesn't study chemistry is 5 out of 10. And we should notice that in each case we've got the probability that the event happens plus the probability the event doesn't happen must equal 1. Now a Venn diagram will help us in the deduction of other probabilities for the events M, E and C. So if we set up our Venn diagram with 3 overlapping circles, we can see first of all that Alan studies maths and chemistry but not English. So he goes in the bit where maths and chemistry overlap but English doesn't overlap. Similarly, Brian studies English only, so he goes in the part of the diagram which just has the E circle, which is there. And we can go through similarly for the other students. Carol is maths and chemistry, David is maths and chemistry, Edward is maths and English, Francis is maths only, Graham is chemistry only. Harrison is maths and chemistry. And Ian doesn't do any of the subjects, so Ian sits outside the 3 circles, and Jane is English only. So looking at that diagram, first of all, the probability of the pupil chosen doing maths and chemistry. Well, we can see that we've got 4 pupils who do both maths and chemistry. That's pupils A, C, D and H. So that's a probability of 4 out of 10. The probability of English and chemistry. Well, English and chemistry, there is no overlap there at all. So that is 0 out of 10. And the events E and C are examples of what are known as exclusive events. If one event happens, then the other one doesn't happen. The probability of M or C, so we want what's the probability the student we pick studies maths, or studies chemistry, or both. So, if you look at the diagram, maths or chemistry or both is F, E, D, A, H, C and G. So that is 7 out of the 10 people. The probability of E or C, well, who does English? We've got E, B and J doing English, and we've got G, D, A, H and C doing chemistry, and G doing chemistry. So altogether there we've got 1, 2, 3, 4, 5, 6, 7, 8 people doing chemistry or English. So the probability of English or chemistry is 8 out of 10. The probability of M dash, so the pupil doesn't do maths and does do chemistry. Well, there's only one pupil who doesn't do maths and does do chemistry, and that's the pupil G, so that is 1 out of 10. And the probability of M union C dash, so that's the probability the pupil does maths or the pupil doesn't do chemistry. Well, the pupils who do maths are F, E, D, A, H and C. So we've got 6 of those. Don't do chemistry. Well, we've got some of the ones we've already included, but new ones are B, J and I. So altogether there we've got 9 people who do maths or don't do chemistry. So the probability of M union C dash, the probability the student picked does maths or doesn't do chemistry is 9/10. If we return to the experiment of throwing 2 fair die, one of which is red and one of which is blue, and let A be the event the total score is 4, and B be the event the score on the red dice is 6, then the sample space for the diagram looks like this. And we can see very quickly that the events A and B are exclusive. We can see that the probability of A, well, we've got 3 ways of obtaining A out of the 36 possible outcomes. So the probability of A is 3/36. The probability of B is 6/36. And the probability of A or B, that's the probability that A happens or B happens, probability of A union B, is 9/36. But 9/36 is exactly the same thing as 3/36 plus 6/36, which is the probability of A plus the probability of B. Now, there is an important result that we will be using lots and lots of times, which says that if we have exclusive events E and F, then the probability of E union F, or the probability that E happens or F happens, is the same thing as the probability of E plus the probability of f. Keeping with the 2 dice experiment, let's now have G be the event the score on the red dice is 3, and H be the score on the blue die is greater than 2. Again, we can draw the sample space diagram for the experiment. So there's the event G, here's the event H, and we have the probability of G is 6 out of 36, or 6th, and we have the probability of H is 24 out of 36, or 2/3. If we're now interested in the probability of G intersect H, so that's the probability that G happens and H also happens, then we can see that only happens in 4 of the 36 outcomes. So we can say the probability that we've got G intersect H is the probability that G happens and H happens, which is 4/36. And 4/36 is the same thing as 1/9. But 1/9 is exactly the same thing as 1/6 times 2/3. So we've got the probability of G intersect H, or the probability that we've got G happening and H happening, is the same thing as the probability of G happening times by the probability of H happening. Now, intuitively, we know that the score obtained on the red dice is independent of the score obtained on the blue dice. And in mathematics, this intuitive idea of independence is formalized by saying that the events A and B are statistically independent if the probability of A and B happening is the same thing as the probability of A times by the probability of B. Now we'll be looking at exclusive events, independent events, and indeed other results about probability in the next video.